In this video, I'm going to do a line integral of a vector-valued function. One nice example of where these line integrals are used is to figure out the amount of work done on a particle as it moves through some sort of force field. In the notes, we show that if we can get a parameterization for our curve, let's say it runs from t equals a to b, then we can solve this by figuring out what our function is along that curve, taking the dot product of that with the velocity. So given a force field, it really just boils down to figuring out the parameterization so that we can figure out the velocity, and then plugging our parameterization into our force field function so that then we've got these two objects we can take the dot product of to get a scalar function that we then integrate. So as a concrete example, let's suppose that we've got a particle that goes around a circle. For these line integrals of vector fields, it's actually going to be important what direction our particle traverses this path. So let's say that this particle goes around counterclockwise, and we'll have it start right here. We can parameterize this the usual way. R of t is equal to cosine of t, sine of t, and t runs from 0 to 2 pi. Later on, we're going to need the derivative of this, so let's work it out now. That's just minus sine of t and cosine of t. For the vector field, let's imagine that f is equal to x squared in the x direction. Or we could write this as a vector as x squared and 0. So this means we've got this force field that's acting only in the positive x direction. Now this equation gives us the force field at all points in space, but for our line integral, we only really care about what this force field looks like along the curve. So let's evaluate that. So along the curve that we've parameterized using r of t, we can just replace our x with our x of t, which is cosine of t, and so this becomes cosine squared t 0. We've already got r prime of t, so now we can compute the integrand of our line integral. In particular, it's f of r of t dotted with r prime of t. And so that's just cosine squared t and 0 dotted with minus sine of t cosine of t. Or just minus cos squared t sine t. Coming back up here, we see that this is what we're going to be integrating from t equals 0 to 2 pi. So the work is equal to the integral from t equals 0 to 2 pi of minus cos squared t sine of t dt. If we make the substitution, u is equal to cosine of t, get the antiderivative and plug cosine of t back in, we'll just get that this is equal to 1/3 cosine cubed of t, running from 0 to 2 pi. And if you evaluate that, you just get 0. So we've got 0 work done here. So that's the answer to the question. We've finished solving the line integral. Can we make sense of this result? Well, if we go back to our curve and imagine what's happening to this particle as it goes around the curve, we see that we do have this perfect balance such that the work should be 0. For example, at this point here, the force is acting in the positive x direction, but that dr vector will be pointing in this direction. Whereas down here, opposite the x-axis, the force is still acting in the same direction, but our dr vector has flipped around and makes a supplementary angle with f to what it did above. So when we take the dot products here, we'll get the same magnitude but opposite sign, which means that the contributions from these 2 points on this curve will cancel out exactly. We'll get similar cancellations happening everywhere else on the curve. So those 2 points will cancel out, these 2 points, their contributions will cancel out, and so on. it turns out for this force field, we could have actually had any closed path. And as long as we came back to our starting point, the total work would be 0. This is because the force field in this question turns out to be something called a conservative vector field. So it won't actually always be the case that if you do a line integral of a vector field over a closed path, you get 0, but it will be true when you're dealing with a conservative vector field. We'll talk about this a lot more as the course goes on. Alright, that's it for this example. Thanks a lot.